Hello and welcome to this new video. Today we're going to talk about a very important device in electronics, but many people don't really know it well. Do you know what it is? It's the oscilloscope. This device is like your eyes in the world of signals. It lets you see electrical signals as if they were animated drawings right in front of you. From frequency to amplitude to timing, everything is visible. Let's get started.
An oscilloscope is another important tool when it comes to analyzing and debugging circuits. They let you see electrical signals, and you often hear it abbreviated as O-scope or sometimes just scope. They're particularly handy when it comes to measuring things like amplitude, frequency, and transient signals that your multimeter just can't catch. In older cathode ray oscilloscopes, the electrical signal under test changed the voltage between a set of vertical deflection plates that caused an electron beam to move up and down as it swept across a phosphorescent screen. But modern digital scopes take measurements using an analog to digital converter to sample the signal and then draw the waveform on a screen. While all these buttons and knobs may seem daunting at first, don't worry, I'll show you which ones you need to care about so you can begin taking measurements. To start, let's look at the user interface. The first thing you'll likely notice when looking at a scope is the display. This is where your waveform and any information about it will be drawn. Here we have two ports marked with colored bands that accept probes with B and C connectors. You'll commonly see scopes with 1, 2, or 4 channels. This one happens to have 2. The vertical section controls the voltage scale on the display for each channel independently. The horizontal section controls the time scale on the screen for both channels. You can manually adjust how the scope triggers with this section, which tells the scope to start measuring when it sees a particular part of a signal. The menu section contains various settings, some of which we'll use later, like saving an image. You'll also be pressing single, run, and stop quite often to start and stop measuring. As it turns out, scope probes are more than just some pieces of wire. The most common probes you'll find are passive voltage probes, which means that they measure the voltage difference between the ground clip and the tip of the probe. There are no active electronics in the probe, just some cable, resistors, and capacitors. If you were to look inside our oscilloscope, you would find that each of the input ports has a 1 mega ohm resistor and a 16 picofarad capacitor connected in parallel from the signal input to ground. Just connecting wires to the port would work for low frequencies, but since they look like antennas, they're liable to pick up noise and inject it into our circuit or measurement. To fix that, we use a coaxial cable to provide extra shielding. Now, if you look at most scope probes, you'll see a little switch labeled 1x on one side and 10x on the other. This refers to the amount the probe attenuates the signal. If you switch it to 1x, it is exactly like our drawing. The tip is connected directly to the inner wire of the coax cable, and the ground clip is connected to the shielding. While this works well for signals with frequencies less than a few megahertz, coax cable can act like a capacitor and add more than 100 picofarads to your test circuit. This can adversely affect many circuits, especially if you're trying to capture higher frequencies. To remedy this, many probes have the option of enabling an inline 9 mega ohm resistor to isolate your circuit from the cable. This is what the 10x setting on the probe does. The 9 mega ohm resistor in the probe and the 1 mega ohm resistor in the scope act as a 10-to-1 voltage divider. It's important to note that 10x does not mean 10 times gain. It means the signal is reduced by a factor of 10. The problem with adding a resistor in line with our signal is that with the capacitance in the coax and scope, it creates a low-pass filter, and high-frequency signals will appear smaller. To fix this, 10x probes include an adjustable capacitor in parallel with the 9 mega ohm resistor used to compensate for the low-pass filter. This will keep the signal attenuation more or less the same across all frequencies. Now, I recommend leaving the probe on 10x as that's the best compromise between signal attenuation and having the probe affect the circuit you're trying to measure. However, that does mean we need to tell the oscilloscope that we're using a 10x probe, and we need to tune the compensation capacitor inside the probe. You'll likely only need to tune your probe once, but it's a good idea to check them every now and then to make sure that the compensation capacitor didn't get adjusted by your lab partner or some spooky ghosts. To start, select 10x setting on your probe and plug it into the oscilloscope. Turn on the scope and let it boot up. We'll need to make some initial changes to the settings. First, make sure channel 2 is off. Press the channel 1 button to see the input settings. Make sure you're on DC coupling as we want to see all parts of our signal. Press the button next to probe, highlight 10x using the top left knob, and press the knob to select it. Press the trigger menu button. Make sure type is set to edge and source is channel 1. Check that slope is set to up edge. These tell the scope that we want to start our measurements on a rising edge of a signal on channel 1. Most scopes come with some kind of built-in frequency generator so you can test your probes and tune the compensation capacitor. This one happens to have a 1 kHz square wave generator we can use. Attach the ground clip to the ground tab and hook the probe around the signal tab. You should see something appear on the scope's display. Now, you'll need to adjust the horizontal and vertical scale knobs so you can clearly see the waveform. Note that turning the knobs clockwise decreases the time or voltage scale, which has the effect of zooming in on the waveform. If you want to move the waveform up or down, you can adjust the smaller knob above the channel 1 button. Just note that this moves the 0 volt level for channel 1 as well. If the waveform seems to be moving or jittering, this is because the scope has no idea when on the waveform to start measuring, but we can fix that by adjusting the trigger level. Use the knob in the trigger section to raise the level to somewhere between the min and max of the waveform. This tells the scope to begin measuring as soon as it sees a rising edge, perform one sweep on the screen to draw the waveform, and then repeat the process. Note that digital scopes like this can store and display information before the trigger. Because this is a periodic waveform, the image appears static on the screen. Now, these highs and lows should appear completely flat, as we assume the scope is outputting a near-perfect square wave. If not, it's because the compensation capacitor in the probe hasn't been tuned, so we're actually measuring the signal incorrectly. Using a tiny flathead screwdriver, adjust the screw head in the probe until the square wave has straight edges. Note that some probes have the compensation adjustment screw near the probe's plug instead.
And that's how we've reached the end of today's video. We took a look at what an oscilloscope is and how it works. Thanks a lot for watching.